Hello. This lecture is about the use of satellites for observing our atmosphere. To begin with, we will look at different types of satellite orbits and why we might use them. We will then look at which observing geometries can be employed, followed by the types of instruments that are used, depending on if we want only daytime observations or 24-hour coverage. Finally, we'll take a look at one of the weather satellites that provide continuous data for our forecasting agencies. First, we need to look at the types of orbit that are usually used for Earth-observing satellites, and how much of the Earth can be observed and how often. Let us consider only circular orbits. That is, the satellite will have a fixed distance to the surface and therefore see all parts of the Earth in the same way. According to Newton's second law, a body will move in a straight line unless a force is applied to it. For a body in orbit, the force necessary to keep it rotating around the Earth is provided by gravity. As you have seen earlier, the force due to gravity on a body of mass m due to a planet of mass capital M is given by gmm over r squared. G is the universal gravitational constant, and r is the distance between the centres of masses. Gravity thus contributes the centripetal force needed to keep the satellite in circular motion. This force is m omega squared r, where omega is the angular velocity, which in turn equals 2 pi over t, the time period of the orbit. Since most of us do not remember the value of the universal gravitational constant, we can remove this by considering the gravitational force acting on a test mass close to the surface of the Earth. Since most of us do remember that the acceleration due to gravity on the Earth's surface, g, is equal to 9.81 meters per second squared. As you can see, the test masses cancel out from both expressions. Combining the expressions, the period of the orbit is given by t equal to 2 pi the square root of r cubed over gr squared. Two types of orbit are typically used. Low Earth orbits, often orbits moving close to pole with typical altitudes of 850 kilometers and thereby periods close to 90 minutes. Geostationary orbits are placed over the equator with altitudes of approximately 36,000 kilometers and a period that matches the Earth's daily rotation. Geosynchronous orbits are similar, but the spacecraft wanders a little in latitude since it is not placed directly over the equator. For satellites in low Earth orbit, the orbit remains fixed in space, and the Earth rotates under it. In that way, the sub-satellite point covers much of the Earth's surface during the 24-hour period it takes the Earth to rotate. As you can see in the animation, the coverage is better near the poles. The repeat time for a single satellite is about 24 hours. A trick can be played by using the fact that the Earth is slightly flattened by its rotation. It is possible that by slightly tilting the orbit to ensure that as the Earth travels around the Sun during the year, the orbit maintains the same angle to the Sun, and thus the observations are always made at the same local time. That is important for instruments that rely on sunlight to measure. These are called sun-synchronous orbits. Geostationary satellites remain approximately above the equator and view about 1/3 of the Earth's surface. They have very good temporal resolution, meaning that they can often give images every few minutes. However, because of the curvature of the Earth, the resolution of the images becomes very bad beyond 60 degrees north and south. So, to provide comprehensive data collection, a combination of both low Earth orbit and geostationary satellites is used. Instruments on the satellite can observe the atmosphere with different geometries. The figure shows two of the most used configurations. Downward-looking instruments are said to look in the nadir. These often sweep from side to side, building up the image as the satellite moves along its orbit. To achieve vertically resolved information about, say, an atmospheric gas, limb viewing geometry can be used. In this geometry, the line of sight of the instrument is often swept up and down through the atmosphere by moving a mirror or the satellite itself. Another geometry that gives good vertical resolution is occultation. This is when we observe an object that could be the sun, a star, or even a GPS satellite as it goes down behind the Earth's atmosphere, often as a result of the motion of the observing satellite. The measurement technique then involves observing how the atmosphere affects the signal from the object. This could be absorption of certain portions of the light or the bending of the signal due to the refraction in the atmosphere. The choice of measurement technique can depend on many things. We may choose to observe 24 hours a day or only during the daytime. We may want to make images, or we may wish to measure the temperature or gas composition. The image of clouds that you can see here is taken in visible light and as such required that the sun be illuminating the cloud tops. At night we would have to use infrared wavelengths, where the atmosphere and the clouds emit blackbody radiation just because they are warm. This figure shows a much more complicated type of data, where the infrared light from a single image pixel has been split into its different wavelengths. Let us see what information can be found in this diagram. First, let us look at the infrared wavelengths between 10 and 13 micrometers. This wavelength region is known as an atmospheric window, and we can see down to the ground. Here you can see that the measured light, or spectrum, closely follows the dashed curve labelled 320 Kelvin. This means that the surface of the Earth in this measurement is emitting infrared radiation like a body with a temperature of 320 Kelvin. In this case, it is the Sahara Desert. If we now look at the region near 15 micrometers, we see that the signal is lower due to the absorption by carbon dioxide. In the center, where the absorption is strongest, the corresponding temperature curve is under 220 Kelvin. We are now measuring high up in the lower stratosphere, which is much colder than the surface. You can imagine that by looking at places where the absorption is stronger or weaker, we can obtain information on the temperature at different altitudes in the atmosphere, assuming we know the amount of CO2 that is present. Near 9.6 micrometers, we can see that ozone absorbs the infrared light. We can use that information to measure the amount of ozone present in the atmosphere once we know the temperature profile. Weather satellites provide the backbone of all our information about the atmosphere. They provide basic information on clouds, humidity, temperature, as well as information on wind from the tracking of clouds. The main suppliers of data for weather affecting Europe are the European Organisation for the Exploitation of Meteorological Satellites, EUMETSAT, and NOAA, the National Oceanographic and Atmospheric Administration in the US. In the figure, you see a schematic of the European METOP satellite with each of the instruments on board indicated. For the atmosphere, the most important ones, clockwise from the top, are GOM2, GRASS, IASI, HERES, AVHRR and AMSU-A. GOM2 is a spectrometer operating in the UV visible part of the spectrum, observing in the nadir, and used to measure ozone and other gases, employing differential absorption. GRASS receives radio waves from GPS satellites as they occult, and by measuring how the waves are bent by the atmosphere, obtains temperature and humidity profiles with high accuracy and vertical resolution. IASI and HERES both operate in the infrared region of the spectrum and use absorption emission spectroscopy to measure a variety of gases as well as the temperature. AMSU operates in the microwave region and also measures temperature and humidity, but because it operates in the microwave, it is much less sensitive to clouds. AVHRR operates in the visible and infrared and gives, among other products, information on clouds both day and night. In this lecture, we have discussed different types of orbits that are used for satellites observing our atmosphere. We have also considered different observing geometries and the advantages of each. We have touched on the techniques employed to provide information on our atmosphere, both day and night. And finally, we looked briefly at the instruments aboard one weather satellite. Thank you for your time. Stay tuned for more lectures about satellites and observations of the atmosphere.